So, welcome back to our video lectures on projective geometry. This time we start a new chapter. We will talk about conics. These are the solutions of quadratic equations in the projective plane. And there is at least a threefold reason why we will have to deal with conics in a certain depth. So, first of all, they are beautiful. Secondly, they are fundamental, so we will need them for various other things. And third of all, they are really important because many other concepts in the more advanced parts of projective geometry really depends on a deep understanding of conics, and for that reason we will spend at least 5 video lectures with the topic of conics. In this first lecture I want to give you, well, first of all the definition. Secondly, I want to talk about projective transformations of conics, and thirdly I want to give you at least a few useful formulas that are relevant in context with conics. Some of you may recognize that part of that was already covered by the Geometriekalküle Vorlesung. So, if we are talking about a conic in our context, we are in a projective plane over a given field, and we are looking for a point set that is given as a solution set of a quadratic equation. So here is a quadratic equation. So I give you 6 numbers A, B, C, D, E, and F, and ask you for the set of all xyz that satisfy this quadratic equation. And you see it's really quadratic in each of the summands here. So in each of the summands you have 2 variables involved. So either a variable is involved twice, like in the first 3 terms, or 2 different variables are involved. And the fact that the exponent is essentially quadratic in each of these terms makes sure that this expression is actually well defined, because if you have a solution of this equation and you multiply the corresponding point by a certain factor, then you will still have a solution of this equation. So it makes sense in our setup where points are actually given by representants xyz of a whole equivalence class of points that differ by a scalar multiple. Okay, and when you think about a picture of a conic, a kind of prototypical thing you should have in mind is an ellipse, and this equation here is for a point being on an ellipse. But please keep in mind that an ellipse as a kind of projectively distorted image of a circle is only one type of conic. There will also be parabolas and hyperbolas, and there will also be degenerate situation where your conic is decomposed in a finite number of lines. So you may have wondered why I have written a 2 in those spots here, and this miracle resolves if you look at a different representation of the conic, and one that we will deal with in most of the cases. So we will write this equation as a quadratic equation in vectors and matrices. So we plug in our point P at 2 places of a simple matrix multiplication and encode this quadratic equation here by a matrix sitting between those 2 occurrences of P. So essentially we always have an equation like P transpose times A times P, and this explains why I've written the letters A and P at this image here. A represents the matrix that gives us the conic, and P represents a given point. So there is an important difference between this matrix representation and this equation up here. In the matrix representation, it could in principle happen that at this slot and at this slot you have 2 different numbers, and the sum of those 2 numbers will occur in the corresponding slot over here. So the xy term comes from the sum of these 2 numbers. The xz term comes from the sum of these two numbers, and the yz terms comes from the sum of these two numbers. And in principle, we can always make sure that our matrix is given in a symmetric way by simply averaging out. So if you are given a non-symmetric matrix M representing a conic, you can simply get a symmetric one by considering M plus M transpose and choosing this as an A. And if you want to have exactly the same numbers, you can divide by 2 here as well. It really doesn't matter, because scalar multiples, as usual in homogeneous coordinates, don't matter. If you scale the matrix A, it gives you the same conic. Sometimes we will also consider this expression here as a function. This function then is called a quadratic form of the corresponding conic. This is mainly a kind of reference also to other books. So now we want to understand how conics behave under various aspects. So we want to understand how they behave under transformations. We want to understand which types of conics there are. We want to understand how to make calculations with conics. And this is what all the remaining part of this and the next lectures will be about. And we will see there is a lot of structure behind that subject. So let us start with transformation behavior. And for that, we consider a projective transformation that maps a point to a different point. And you may remember projective transformations on the point level were given by multiplication with a matrix. And you may remember we extended this transformation to lines as well in a way such that incidences are preserved. So we figured out how we have to change the homogeneous coordinates of a line in order to preserve incidences between points and lines under projective transformations. And the main idea here was that the m and the inverse of n should cancel out in the equation. Now we have a conic equation, and we have to understand how should we transform the conic equation. And the secret to do that is to multiply from both sides with the inverse of m, making sure that we transpose on the left side here. And this equation also preserves incidence. And if you don't believe that, here's a very simple proof of that fact. So take a point, a conic, and the point again after the transformation, and we check that the condition that the point is on the conic after the transformation is the same as the condition of being incident to it before the transformation. So simply plug in the definitions. So here you have your transformed point, here you have your transformed conic, and you have your transformed point again. Reshuffle the multiplication order, and you will see that this here and this here essentially cancel out, and you end up with, well, everything that's left. And this is the matrix A, the point P transposed, and the point P down here, which is our original incidence relation. So this kind of transformation preserves incidences. So now we can do something that we haven't done for other objects yet, because it simply was not necessary. We can try to classify types of different conics with respect to projective transformation, because it will turn out that there are different types of conics that cannot be transformed into each other by a simple projective transformation. And for that, we will use projective transformations to get a kind of normal form of a given conic. In linear algebra, you learn about principal axis decomposition of symmetric matrices. So assume that A is a symmetric matrix. So this will be the case in our conics situation. Then you find a matrix R with the property that if you multiply R from both sides to the matrix A, you get a diagonal matrix D. So matrix R is special as well. This matrix is an orthogonal matrix, meaning that its transpose is its inverse, and so A and D are similar, and in addition you can make sure that the matrix D has only real entries. If you combine this with our knowledge about transformation of matrices, you see that you can take the matrix R transposed to be the matrix M to the minus 1 here, and the matrix R then is M to the minus 1 transpose. And by that, you can say, well, let's consider a projective transformation for a given conic that sends point P to a point R times P, and this projective transformation will send our conic to the conic that I've written down here. And if you check that, R to the minus 1 is R transposed, so you get exactly this expression over here, and you see that this here is in fact a diagonal matrix. So up to projective transformation, every conic is equivalent to a conic only given by a diagonal matrix, and geometrically this corresponds to the fact that our conic is oriented in a way such that it is aligned to a nice coordinate system here. So can we get further? So we still have our numbers alpha, beta and gamma in the representation of this diagonal matrix, and we know these are real numbers. And next thing that we can get is we can make all these real numbers to be either +1, -1 or 0 by simply doing the following thing. We again apply a projective transformation, and we can rewrite A by multiplying with those matrices here that allow us to change the numbers at the diagonal here to entries which are only -1, 0 or +1. Actually, we cannot turn a -1 into a +1 or a 1 into a 0 because we have to multiply from both sides. And this gives us a quadratic term in the prefactor, which means that we only can multiply with positive numbers, at least if we are over the real numbers here. So, but anyway, that's a good thing. So after that, we are left with the situation that we are not only aligned to a coordinate system, but we only have to consider very, very, very few shapes of our conic. And so what we essentially get is a situation where we only have +1s, 0s and -1s here, and in case that we have only pluses or minuses, it may still happen that we either have a circle or a kind of standard hyperbola, and this standard hyperbola may also be oriented in two different ways. And to get rid of that, we can still apply another type of projective transformation. If you multiply by these matrices here, observe they are their own transposed situations, they simply interchange the first two entries of the diagonal matrix. If we had a sigma alpha here, it will after that transformation be here, and a sigma beta here will after this transformation be here, and by that we can change the order of the pluses and minuses that occur. So if we take all that together, we find that if we want to do a classification of types of conics, that up to projective equivalence, we are left with only 5 different cases, and they come from the different sorted distributions of zeros, ones, and minus ones in our matrix. So here are the 5 types that we get. So it's the matrix all one, then 2 identical signs, 1 opposite sign, 2 identical signs and a 0, 2 opposite signs and a 0, and 1, 1 and 2 zeros. You may wonder why there are not more types, like something like minus, minus, minus. But remember, a scalar multiple didn't change our conic, so a matrix A and minus A just give us exactly the same conic. So I can really focus to the situation where I have a plus 1 in the first spot. So let me write down the equations that you get in each of those cases. Here you get something like x squared plus y squared plus z squared equals 0, x squared plus y squared minus z squared equals 0. Now you don't have a z term, so you just have x squared plus y squared, and here you have x squared minus y squared, and finally you just have x squared here. So let me try to draw pictures of what you see here. And if you try to do that, you will first struggle with the first matrix here, because the only real solution of this equation is 0, 0, 0, and 0, 0, 0 was not a vector in our system of projective geometry. So as a matter of fact, this case here does not have any real solution. It only has complex solutions. Later on we will have to do with complex projective planes as well, so at that point you should memorize no real solutions, but you still have complex solutions. This one here is better. It's a kind of generic circle equation. So if you set z equals 1 in the standard embedding, then you just have x squared plus y squared equals 1, and the drawing that you get is a unit circle in the standard embedding. You may consider this as a prototype, as a real non-degenerate conic. Everything that you usually consider to be a non-degenerate conic is up to projective transformation a circle. Now things get interesting because you get zeros in here, and we enter the realm of degenerate situation. So the first case is something like x squared plus y squared equals 0. And again, you may think, oh, there are no real solutions. As a matter of fact, there is one real solution of that. You get 0, 0, 1 as a real solution, so just 1 point sitting in the center of the standard embedding. And actually, if you look at this conic, you see it's just this 1 point, but this 1 point lies on the intersection of 2 complex conjugate lines. So over the complex numbers, you really have 2 solutions here. So here again, you are in a real situation. You have 2 real lines that intersect at a point, and the 2 real lines are x equals plus y and x equals minus y. You can simply check that this is the case. And now it may happen that these 2 lines even coincide, and then you get what people call a double line. It's a kind of constantly double solution of a quadratic equation on an entire line, and in that case this entire line is given whenever x equals 0, which means you have the y-axis in the standard embedding as double lines. So let me give you one more picture of what's going on, and for a moment focus on the real non-degenerate case, and I want to show you how you can geometrically think about conics as really literally conic section. So what you have to do is you have to take a double cone like you see here and intersect it with a plane, and the images that you get as a kind of intersection correspond to conics. So let me move that situation a little bit. Let's twist this conic and watch at these intersections that you get here, and you see, if you consider this here as the standard embedding of the plane, you get nice pictures that resemble conic sections. Let me have a look at those graphs that you get here, and in particular count the intersections with the line at infinity. So you see this curve here may intersect the line at infinity, or it may not intersect the line at infinity, and counting the number of intersections gives us another way to look at conics. So here we are in the case that we have a curve that goes to infinity, touches the line at infinity and comes back, and it turns out this is in fact a parabola. So in a parabola you have the situation, the conic section goes to infinity, touches infinity and comes back. If I rotate my conic a little bit further, then you see I get two intersections, and the picture of what you get is in fact a hyperbola. So here you see the hyperbola from the top perspective, and guess what? If you rotate further, you get a curve that does no longer intersect the line at infinity, and this is an ellipse. So if you take this picture, it's a kind of sub-classification for the standard embedding of the real non-degenerate case. So this just corresponded to this one part in our diagram where you had the entries 1, 1, minus 1. So let me go back to the general classification and now focus a little bit on the situation of degenerate conics. And I want to give you a deeper understanding of degenerate conics now. So if you have a degenerate conic, it can be expressed as a curve that can be decomposed in two lines, which even may coincide. And if you consider one equation of such a line and a second equation of such a line. So assume that we have a line with homogeneous coordinates L here and with G here, then each of those lines is given by a scalar product equation, and if we want to combine those two lines to a conic equation, we can simply multiply them. So any point P satisfying this equation is either on G or it is on L. And now the question is, how can we derive a matrix from that? And here's a kind of cooking recipe. First of all, rewrite your scalar products here as kind of vector multiplications with transposes here, and do it in a way such that you use the P transpose here and the L transpose here, and then reshuffle the multiplications and put G times L transpose together. So remember, both G and L transpose were three-dimensional vectors, so this here turns out to be a 3x3 matrix. Unfortunately, this matrix in general is not yet symmetric, but you can symmetrize it by the trick I taught you earlier, by simply adding it to its own transpose, and we can write it in this nice formula here. And this here is the matrix A of the conic that you see in that picture, and it turns out that this matrix either has rank 1 or rank 2, depending on the question whether those two lines coincide or not. So if you look at the matrices on that page. Here you have a matrix. This matrix always has rank 1, but if you symmetrize, it may have either rank 1 or rank 2. And so let me look for the two cases that may happen. So it may happen that those two lines coincide. Then as a matrix you get twice this rank 1 matrix, and so in that case you get rank 1. And in the rank 2 case, I give you a concrete vector that you can multiply to that matrix here, such that you will get a 0. And the concrete vector that you get here is actually the point coordinate representing the intersection of those two lines, because if you take this expression and multiply out, you can rewrite that as L times a certain scalar product plus G times another scalar product. And if you look at those two scalar products, you see, well, actually, with the usual formulas of linear algebra, these things are determinants here, with one letter occurring twice in both cases. So after all, this has to be a 0. So you get a non-trivial linear dependence on your columns of the matrix, and this proves that you have a rank 2. So, I want to use that as a kind of final remark of this section as an indication of how you can take the rank of a matrix to conclude something about its degeneracy type. So if you have a symmetric 3 by 3 matrix and you observe that this matrix has a full rank 3, then it cannot be decomposed in two lines, and it must be a full dimensional non-degenerate case. So either you are in the case where you have the real non-degenerate conic, or all solutions are non-degenerate and fully complex. In the case that you have a rank 2 matrix, we just saw that it decomposes in two lines, though these two lines can either be real or they may be complex. In both cases, their intersection is a real point of our conic, and actually this real point can be calculated by intersecting those two lines. And in the rank 1 case, you are in the fully real case where you have a double line here. So much about the classification. In our next slot, I will explain how degenerate conics can be nicely used to calculate a conic through 5 given points. See you there.